One of the more unusual, or at least unexpected things for me as I was going through the SENS publication list was a couple of publications that were talking about the extracellular matrix, like collagen,
Okay.
um, uh, like cross-linking and a process called glycation. That's very intensive biochemistry. But uh, like that has a role with tendons. I assume that there's like other tissues in the body for which elasticity also matters. So, in terms of like this physical property of elasticity, I don't know. Can you maybe go through that and
Sure,
like
totally.
like
I
talk?
should
Yeah.
probably Sure, and I should probably go through it in a little bit of detail because it doesn't get much attention these days. Fundamentally, the reason why it doesn't get much attention is because the people who wrote the Hallmarks of Aging paper that I mentioned earlier back in 2013, they just left it out. You know, when I first saw that paper, I was completely horrified. And I wrote to all the authors and I said, listen, great job. Thank you for restating what I said a decade ago, except the word glycation just doesn't feature in your whole paper at all. What the fuck? Um, and one of them wrote back and said, yeah, we really should have had 10 hallmarks, shouldn't we? But there you go. Anyway, so yeah, there is this process, a chemical process by which the proteins uh, that compose this thing called the extracellular matrix that gives our various tissues their elastic properties, those proteins react with sugar that is in the circulation. And usually that's harmless, then in fact it is spontaneously reversed. But occasionally that doesn't happen. Occasionally and actually it's really baroque with a lot of biochemistry. There are whole conferences about this one thing, right? Um, but yeah, occasionally you get additional cross-links, chemical bonds between proteins that were previously not bonded together and therefore were able to slide against each other. And that's where the stiffening happens, the loss of elasticity. And it's essentially the same reaction all over the body. So the places that are most interesting really are the skin. This is a big part of why we get wrinkles. The skin is less elastic.
Huh.
The lens of the eye, that's why we can't see close up so well when we're older, because the lens becomes less elastic, can't be deformed and squeezed by the extraocular muscles in the same way to change its focal length. But of course, the big life-threatening one is the major arteries. A large part of why we have higher blood pressure when we get old is because of this stiffening process. Essentially, the heart has to beat harder in order to push the blood around when the energy is not being kind of buffered by the elasticity of the major arteries.
Right.
And yeah, it's a big deal. So we've got to do something about it. Now, the chemistry of all of this was largely worked out a long, long time ago. And that's when everyone gave up because they rapidly came to the conclusion that the particular structure, this thing called glucosapane, which is the major type of crosslink, the most abundant one that accumulates in humans, is actually just unbreakable. There's no way we're going to be able to develop a drug to chop it in half and thereby restore the elasticity. Now, that's not because of side effects. Because one piece of luck that we have here is that the chemical structure of these crosslinks is very different from anything that the body lays down on purpose. In particular,
Hmm.
glucosapane has a seven-membered ring in it, which is not the kind of thing you tend to see in biology textbooks.
I
Right?
don't recall ever seeing a seven-member ring. Huh.
Indeed.
There you go.
So, indeed. So that's not the problem. The problem is thermodynamics. It's just not very reactive. You need a reactive molecule to react with it, and reactive molecules tend to be, not terribly specific. So it took a while for anybody to really pay attention to this. We worked in the end with a really fantastic group of organic chemists in Yale, in New Haven, Connecticut. Um, and they cracked it. They figured out, first of all, how to actually quantify and detect glucosapane. And that was largely because they also figured out how to synthesize it on purpose in large amounts. Normally, before that, you would have to isolate it from aged collagen, and then you would only get the most extraordinarily trace amounts and not enough to be able even to raise an antibody. Um, and it would be incredibly laborious. Now you can make gram quantities of it really quickly for pennies, so that's no longer true. Um, Oh, so that's good. So then they were able to take the next step and find enzymes that were able to break these things down. Now, enzymes may not be the final solution because they may be so big that they can't get to the crosslinks properly. There's something called steric hindrance that happens there. But it's a start. It's enough of a start that project, that work at Yale has now been spun out into one of our startup companies. So that's all wonderful. And I think it's quite likely to be able to get to the clinic in the next year or two.
Right. Was that Revel?
Yes, that's Rebel Pharmaceuticals.
Gotcha. Cool. That is awesome.